So we're going to take a bit of a side step from statistics and we're going to come to physics. I'm doing this purely because there is an exam on Thursday on this topic. So this is level 1 physics. Earth and space science is what it's being called now. So it's this special sort of physics of everything with a bit of astronomy and ecology and everything you want. This is one of the two standards, demonstrate understanding of energy in the physical system. And this is from 2023, and this is a pilot assessment. So they kind of did this and tested whether it worked and whether students could do it. And it had a limited release, but it is actually a pretty good exam actually. It gives a pretty nice rundown of what physics of energy is. So without me yabbering on, let's get on to it. So here's the equations that you're given. They don't give you much, but they give you enough. So let's kind of go through it. So this is change of energy as power times time. This E subscript K is kinetic energy, half mass times velocity squared. If you're doing calculus and a bit more physics, you know where we get that from. E sub P is potential energy, and it's in this case it's gravitational potential energy. So things have potential to move when they're at an altitude, but it doesn't become kinetic energy until it starts moving. This is where the V bit, the velocity bit, comes from. So the amount of potential that some object has is the mass times the acceleration due to gravity, which is given down here. At this level, we say it's 10 newtons per kilogram. Next year, it's 9.8, and it's also equal to meters per second. It's an accelerating, not force, but it's an accelerator. And then year 13, it gets refined even more. It's 9.81 meters per second equals newtons per kilogram. So it's the amount of force that gravity exerts on some weight. So kind of just take this as a given. It's given to you. This delta H here means change of height. So if we start here and we raise something to here, maybe we start here and we raise something to this level, this is going to be the change in height. Okay, so delta just means change. It should be a capital, H should be a lowercase h. Change in height. So the higher something goes, the further it is to fall. And the further it is to fall, the more kinetic energy you'll have. One basic thing in physics is that the potential energy at the top is equal to the kinetic energy at the bottom. So things fall and hit the bottom. Now remember, it's not the fall that kills you, it's hitting the ground that does that. So what falling does, gravity converts gravitational potential energy into kinetic energy, the energy of moving things. You'll be doing these quite a lot later on. W is FD, so W means work. And rather annoyingly, it's a W because one of the other units is also a W. We'll get to in a second. But this is force times distance. So the amount of energy that we need to expend moving something, applying some force over some distance. And because of the mathematics involved, look at the video that I put out, this W is in joules, which is the same unit as energy. Okay, I'm going to skip these two for now. But this one here is power times voltage times current. The reason current is an I is because C was taken. That's pretty much it. P is power, and annoyingly power, the unit for power is the watt, which is often just denoted as W, which is not to be confused with work, which is measured in joules. It's a bit of a pain in the neck, I know, but we've only got 26 meters to play with. This one here is Ohm's law. It says the voltage, that's the sort of the strength of an electrical current. It's the potential difference between 2 points technically is equal to current times the resistance that current needs. So that's the formulas they give you, and let's get on with the questions. So let's do it to it. Question 1. Jamie plays with his football while he waits for his bus. I guess his football is right there. There is always that kid, isn't there, who has a football. Every class, there's always some kid who carries a football. Okay, so we have our bunch of guys. They've obviously absolutely haven't been told to pose like that. And they've been told, just don't look at the camera, don't look at the camera. And taking the camera, and they've taken the shot. Here's the football, and I guess this is Jamie. Doesn't matter. So he throws the ball vertically up. Why, I don't know. The ball has a mass of 0.150 kilograms. So right away we see that mass is already in SI units, it's already in kilograms, so we get that down. And it reaches the height of 3.4 meters. So we're going to say that the change of height is 3.4 meters. That's already in kilograms. So it's already in a form that we like. And its velocity just before it hits the ground, velocity is 7.8 meters per second. So it's already in SI units. Yep, well, we're good to go. Okay, in the box below, write an equation to show the energy changes taking place when the ball falls back down from its highest point. So this is the point I was making before. We start off with gravitational potential energy. People who tell my handwriting is terrible, so I'm trying to later. So gravitational potential energy becomes kinetic energy. So the energy that moving things have. Plus a bit of heat. There will be some sonic energy, some sound. Maybe even the pavement absorbs some shock, but only a tiny, tiny, tiny bit. This bit here is always in any physics. The technical word for it is entropy. So there's never a completely, totally efficient process in physics or in chemistry. You're always never going to get 100% of what you have. You're always going to lose some, whether it be to friction, to heat, to whatever. You're never going to have a perfect experiment. So for that reason, the elastic potential energy is always going to be slightly greater than the kinetic energy, because some of it is lost. And I think the next question actually addresses that. So it's a really important concept to grasp. It's never 100%. So now they want us to work out exactly what we said before. So calculate the average force of friction. So we're going to have some force, and it's going to denote it lowercase f friction between the ball and the air. So when the ball is at the top, it's going to start falling downwards. It's going to collide with air particles, and it's not going to be much of a problem for a football. But if you're flying in a supersonic jet plane, it's going to be a big problem. It's going to heat you. It's going to heat your plane up. It's just drag friction. Okay. Begin by your answer by showing that on its way down at this highest point, 0.537 joules of mechanical energy are changed into other forms of energy. So it's going to be heat, sound, etc. Okay, let's show that. So the gravitational potential energy at the top is going to be equal to the kinetic energy at the bottom plus other stuff. And we want to know what this other stuff is, and it's 0.537 joules. Okay, so let's work out the potential energy at the top. So remember the formula for that: mass times gravity times change in height. Well, we know the mass. The mass is 0.150 kilograms, already in SI units. Gravity, we're given that it's 10 newtons per kilogram, and change of height is given as well, I think, 3.4 meters. So the meters, they're all in SI units, so we can proceed. So 10 times gravitas, so times gravity times 3.4, they're out of order. And we grab our trusty calculator, work it out. So 0.15, so that's the mass, times gravity, we're going to say that's 10, times 3.4 meters, is going to be 5.1 joules. 5.1 joules. That's the line. So 5.1 joules. Okay, now let's work out the kinetic energy at the bottom. And the formula for that, if you go to your formula sheet, is half mv squared. I'm not going to go into where this half bit comes from. Why it's squared, we're just going to take this given. Okay, so it's going to be half times the mass is going to be the same, 0.15 kilograms, 0 there, times the velocity. Now the velocity is also given to us, 7.8 meters per second. It's already in SI units. So it's 7.8 meters per second. And we grab our calculator and work it out. So half, so 0.5 times 0.15 times 7.8 squared is 4.563 joules, which is less than we started. So the change in energy is going to be what we started minus what we ended with. And you can't create energy or destroy energy, you can only change its form. You're even anyway. So let's grab our calculator again. So 5.1 minus 4.563, and we get, drum roll, 0.537, which is what we're testing for. 0.537 matches up perfectly. Physics works. How about that? But are we done though? Actually, just reading the question, we're not fully done because they want the force from friction, don't they? So for this, we can use the work equation. So work is equal to the force times the distance. And remember, the work and energy are interchangeable. Work is just the energy that you do. So gravity is doing this work. It's doing so many joules of work. How much work? Well, 0.537 joules is equal to the force from friction, which is always in the opposite direction of where we're heading, times 3.4 meters, which is the distance. So the force from friction is going to be 0.537 divided by 3.4, which is going to be some number, divided by 3, 4, 0.158. 0.158 what? Well, 0.158 newtons, which is the unit for force. All right, now we're done. So now we're told that 80% of this energy is converted into heat. And that specific heat capacity of the ball is 8,200 joules per kilogram per degree Celsius. Calculate the rise in temperature of the ball as it falls. All right. So first off, we need to work out how much 80% of this 0.537 is. So 0.8 times 0.537 joules is going to be equal to some number. 8 times 0.537, 0.4296. Keep that 6 in there for now. And it's going to be joules. All right, so that's how much heat energy goes into the ball. And now we need some formula that links the change in temperature with the energy. And we know that because it's given to us, the change in energy is equal to MC, change in temperature. Treat this delta and the T as being married to each other. It's change in temperature. Mass is known. Energy is known. The C bit is how much energy we need to put into the ball to heat it by 1 degree Celsius. And it's given to us as this really big number. It's usually a really, really big number. So we've got that. And the only thing we're looking for is this change in temperature. So now it's no longer a physics problem, it's an algebra problem. So 0.42 6 is going to be equal to 0.15 times this 8,200 number times the change in temperature. We want to solve for change in temperature. So let's multiply these two terms first. Let's do the algebra. Oh, that was dramatic. So 0.15 times 8,200 is 1,230 times the change in temperature. So therefore, we divide both sides by the 1,230. We get the change in temperature. The change in temperature is 0.4 1296 divided by 1230. So this is going to be a pretty small number. 0.4296 divided by 1230 equals a really, really tiny number. So it's 3.493. It's like 3.49 times 10 to the minus 4 degrees Celsius change. So I doubt whether there are many instruments that will be able to measure that much change in heat. So 0.123 It'd be another 0, wouldn't it? Change in temperature. So tiny. Tiny for a football, big problem if you're moving really, really fast. So this one is a writing question. So after some time, Jamie's bus did not arrive. So he must live in Auckland or Wellington. Jamie shoulders his backpack and walks to the train station. Okay, so on his way to the platform, he climbs a flight of stairs. This guy lives an exciting life. In terms of work and energy, explain why each of the following three statements, given is true, no calculations are needed. Okay, state 1, no work is done on Jamie's backpack when Jamie is standing at the bus stop. So Jamie might feel the weight of the bag, and effectively he's adding the normal force against gravity. But technically, in physics terms, work, handwriting again, work requires movement. So his legs might be getting tired. He may be actually even burning calories, like standing and keeping this weight up. And unless it's moving, it doesn't work. So the change in energy is going to be mg, change in height. So unless he's changing the height, he's not doing work. Gravity's not doing any work either, unless something is moving. So live with it, Jamie. Okay, no work is done on Jamie's backpack. Jamie walks at a constant speed on horizontal ground. Okay, so this one here, if he's moving at a constant speed, so if he's moving at a constant speed, he's not accelerating. So he's not increasing or decreasing, so he's just kind of coasting along. It's not technically true because his legs keep having to accelerate him every step, but we'll sort of imagine he's like a robot Jamie, and he has like a wheel instead of legs. Okay. Force is mass times acceleration. And if acceleration equals 0, then there's no force. No force, there's no work. Because work is force times distance, and if force equals 0, the work equals 0 as well. I know it says no maths, but there we go. The next one is cut off. So stay at part 3. Part 3, he is doing work on his backpack because he is changing the height that his backpack is moving from here to here, presuming that he's not the Hunchback of Notre Dame. So his backpack was here and now it's up here. So now there is a change in energy, and it's mg, change in height. So he is doing work, He's fighting against gravity. He's expending energy to overcome the gravitational field of the Earth by moving his bag. Not a lot, but he's still doing work. All right, now we get to the electricity part. Electricity and energy. So Jake, I don't know, is Jake one of the guys in the bus? I don't know. He uses three 1.5 volt batteries. Well, he uses 1.5 volt cells in a battery. The torch, so it's 4.5 volts in total. The torch has two lamps, each rated at 4.5 volts. So that's what they'll take before they break. And the current through each lamp is 0.5 amps. Calculate the resistance of each lamp. Well, they're in parallel, so each of them is their own little circuit, and we can use Ohm's law for that. So we know what the voltage is, it's 4.5. We know what the current is, an amp's at 0.5. We don't know what resistance is, but we can work it out pretty easily. So 4.5 volts is going to be equal to 0.5 amps times the resistance in each lamp. Although this A here is an amp meter, it's not a resistor. There are only two resistors here, 1 and 2. This is really just showing you that there's an amp meter there. So now it's a matter of just rearranging. So R is going to be equal to 4.5 divided by 0.5, which is 9. 9 what? 9 ohms. So that's how much resistance, and they're parallel, so they both have 9. Okay, the batteries power both lamps simultaneously. Explain why both lamps glow with their rated brightness if connected as shown above. Okay, so the type of connection, it's a parallel. It's a parallel circuit. So the total resistance is going to be equal to the resistance of 1 over the resistance of 1 over the resistance of the other one. So each lamp is essentially as its own circuit, so it gets all the voltage. Something like that. You would get points probably for saying it's parallel circuit if there isn't a voltage drop in that type of circuit. I think that's probably all you would need to say, or some variant of that. The next question requires a bit of algebra. You remember at the beginning it gave us these equations, and we're going to need to use them to answer this question. So calculate the amount of electrical energy used by both lamps in 2 hours. So that's not an SI unit in hours. Begin your answer by calculating the power output of each lamp. So the power output we're going to work out using this. We know what voltage is, we know what current is. So the power outage of each lamp is the voltage times the current, and voltage is 4.5, it's in parallel, so they get all the voltage, times 0.5, which is a number 2.25, which is calculated 2.25 watt, it's power, so it's watts. I tend to do like a little line there so I can tell that it's watts and not work. 0.225 watts. But what is a watt? So what is a watt? Well, a watt is 1 joule per second. So in other words, these lamps, each of them is using 2.25 joules every second. So to work out the total energy from one of the lamps, we're going to need to multiply this by the number of seconds in 2 hours. Well, if there's 2 hours times 60 minutes times 60 seconds, because remember it's joules per second, we get some number. And we can grab the calculator. 2 times 60 times 60 is 7,200 seconds. Right, so if we're using 2.25 watts, 7,200 times, what's the total amount of energy? And if you look, it's actually this little equation here that we're going to use. So it's going to be 2.25 times 7,200 seconds. It's going to give us some number. Off to the calculator we go. We wrote 7,200.25. So 16,200. Are we done? No. Use them both lamps. So if they're both in parallel, they're both identical lamps, the total energy used up is going to be twice that. Right, which is going to be 32,400 joules, which is, what's that, 32.4 kilojoules. That's our final answer for that. Nice question, yeah, to combine everything together to get an answer. I like that question. So now Jake's torch uses incandescent lamps. You don't see very many of these nowadays, but when I was your age, kids, this is all we had. So what happens is the electricity goes through the coils, and they're made from tungsten. So they're coiled and they're coiled around themselves again. So there's a very, very long tungsten coil, and when you turn it on, the electricity goes through it, it heats up. It heats up so much that it glows white hot. So there are three things that this tungsten needs to have. This is going to be the answer that you're going to need to put. First thing it has is high resistance. Okay, high resistance means high temperatures. So you want it hot enough so that it glows. Fair enough? Power, incidentally, is calculated as the current squared times resistance. So if the resistance goes up, the power output must also go up if current is kept constant. So the power output is high if there is resistance from the wire. The resistance is usually something you try to avoid often in circuits, but with a light bulb we're actually going to exploit that resistance to turn the heat into light. Okay, the second thing that the tungsten has is a small specific heat capacity. So this means that it heats up fast. It heats up fast and with not much energy. So this is what you want in a light bulb. You don't want to put much energy through the light bulb. You want to put enough so that it lights up. You want it to light up quick because it's an AC circuit, so the thing is changing direction 50 times a second. You don't want to be hanging around waiting for the light bulb to heat up before it works. You want to flip that switch, and you want light straight away. Muhammad Ali once said that he was so fast that when he turned the light off in his bedroom, he was in his bed before the room got dark. He was that fast. So you want light fast. The last thing that it has is a high melting point. So you want it hot, but you don't want it to melt. Okay, you want heat, but you don't want melted metal. So it's actually quite a beautiful thing that you're doing with this light. You're heating this filament up just enough so that it glows, but not hot enough so that it melts. It's usually brilliantly clever, but they don't make them anymore. So there you go. One thing I forgot to mention about this really brilliant process is the bulb is this shape, partially to expose as much of the tungsten as possible so you get light all around. It's also pretty close to a vacuum in there. There's a vacuum in there, so there's no oxygen because things combust in oxygen. So you want the light to give you light. You don't want it to catch fire and burn out. So that's the reason why tungsten lasts so long, is because it's in a vacuum tube and it doesn't oxidize. All right, question 3. Pearl has an air conditioning unit installed in the room. The AC unit uses electricity to cool down air and blow cool down air into her room. Just in case you are a caveman and you don't know what air conditioning is. This way, Pearl's room is comfortably cool, although it is hot outside. AC units are typically mounted high up on the wall. I never really thought about that. I just thought it was just more efficient to put it there and to keep it away from those damn pesky kids. But I guess that makes sense. So in the diagram below, draw labeled arrows to show the movement of warm air and cool air in the room. So let's do the warm air. So the warm air is going to rise. It's going to want to rise and expand into more space. And then the cool air is going to sink. That's it. It's a circle of life. Yeah. Okay. All right. So Pearl checks the room temperature on her phone. It's 22 degrees. 2 minutes after she starts the app, she sets the AC to 18 degrees Celsius, so it wants to get to 18 degrees Celsius, and so she turns it on here. It's 22. The AC turns on and immediately starts lowering the temperature down here to 18. So you don't get a free lunch in physics. The air conditioner has to do work. So in order to take energy out of the air, it's got to use energy to do that work. So this is what they're going to be asking us to do now. So Pearl's room contains 41.4 kilograms of dry air, and the specific heat capacity of dry air is 718 joules per kilogram. So we need to remove 718 joules for every kilogram of air that's in the room. Another way of sort of thinking about heating things and cooling things down. If we want to heat it up, we need to put 718 kilojoules into that air. Okay, using this information, calculate the average power of the AC unit. Hate how the AC can sound like alternating current. After she sets it to 18 degrees Celsius. Right, so again, we're going to go to the formulas. And the formula that we're going to use most is going to be change in energy is MC, change in temperature. That's a drink bottle just popping there. So we know most of the stuff. We know the mass, it's 41.4. The specific heat capacity is given as 718. And the change in temperature, we can work out. It was 22 when we started, and it's 18 when we finished. So hopefully we don't need to calculate that. So it's going to be a change of 4 degrees Celsius. Again, I hate how they use Celsius, should be in Kelvin. Okay, that's the first part. So let's work that out now. So let's grab our calculator, and we know the mass is 41.4 times the specific heat capacity, 718, times 4. Now, we're not worried that it's a -4 or +4, it's just a change of 4. So we grab our trusty calculator, clear it, 41.4 kilograms of air times 718 joules for every kilogram times 4 degrees, and we use a lot of energy. So we use all of the energy, and that's 118,900.8, and that's going to be joules. That's a lot. Okay, but it doesn't ask that. It says the average power that's used. Okay, well, there's a few sort of tools that we can use. So if we go up here to our, we've got here, we can use this equation, and we could use the work equation. Let's use let's use this one. So the change in energy is going to be equal to the power times the change in time. Now, little t is time. Big T by convention is temperature. By convention. We know the change in energy, it's going to be this. We don't know the time, but we can work it out. It's 2 minutes. So it's going to be 120 seconds. That's my sister. My dog is barking in there. So you go. Hang on. Oh, anyway, now that I've moved my sister's exercycle, let's get back to physics. So I've done physical work. So we know that the change of energy is this, and we know the change in time. So now the only thing we need to find out is this. And it's going to be pretty easy to find out. So that the power is going to be the change of energy over the change in time. And it's the definition of power. So that's going to be 118,900, put the 0.8 in, over 120. So that's going to give us a number. So it's already in there. Divide that by 120. And we'll get 990.84. What? Well, exactly what? Watts. Which I guess we could come through significant figures. 991 watts. That's how much power is being used by the air conditioning unit. Quite a bit. At night, when it gets cold outside, Pearl closes the curtains on the window in her room. Pearl's curtains reach down to the floor and are close to the wall, explaining why the layer of air acts as an insulator. Now, so here we have kind of the outside world. Let's do moon, the stars, and all the rest of it. So it's cold outside. Here's the window, and here is the curtain. So the curtain goes down to the bottom. So remember what temperature is. Temperature is the average energy of the air, the average sort of movement of the air particles. And what we're doing here is we're creating kind of a void that sort of absorbs that, and it's an insulator. So heat can hit it, and it will not sort of pass the parcel and go outside. So it'll sort of go there and either be absorbed or bounce off. This gap is really, really useful gap. Your homework, should you choose to accept it, is go to McDonald's. I don't know if anywhere else, but especially McDonald's. And McDonald's has their coffee cups kind of look like this. So they'll be that shape, and there will be a small gap around the coffee. It's the same principle. The heat that's in the coffee is going to be hitting the sides, and it can't pass through that air gap and make it outside. It's the same thing with the curtains. The heat is trapped inside, it has nowhere to go, so it has to stay there or bounce off. It can't pass over this insulating membrane of air. Collision theory. So the particles, if we sort of imagine particles, so our world hits a particle there and hits another particle there, it's a bit like the Newton ball. It has nothing to hit here, so it has nowhere to go. So the energy stays inside. And we're done. That's the end of the exam. It's a pretty good exam, actually. Yeah, so apologies for the dog and my sister and the exercycle. Cricket's on as well, so things keep pausing the video to watch that. Oh well, good luck with your exam.